Thank you very much. And first of all, many thanks to Sujay and to Samir for organizing this really nice workshop and for inviting me. And as you know, it's a particular pleasure for me to be here and to be able to be here. My take on mock modular forms is really a geometric one, and that has to do with my background, of course, and also with the fact that the first time I met mock modular forms is a good 15 years ago, when I think they weren't even called that yet. Or we didn't know that what we were looking at were mock modular forms. I was starting to talk to Antarmina about the characters that play a role in K3 conformal field theory. We were getting a headache dealing with modular transformations, and of course that's what mock modularity is about. So that's still somehow my view on mock modularity, and today this talk is going to be a preparation for Anne's talk. It's next after mine, where we try to make a contribution to understanding this new moonshine, Mathieu moonshine phenomenon for M24, which Jeff has already addressed yesterday a little bit. And of course there's still more mysteries than solutions in the context of M24 moonshine, and my belief is that at the end of the day, geometry will play a role in explaining what is going on there. Conformal field theory will play a role, and maybe really we should step back a little bit and take a closer look at the ingredients of M24 moonshine, and in particular the elliptic genus from which it really all began. So the elliptic genus will play center stage in this talk. I won't present any results. I will kind of present a summary on my view of the story with the elliptic genus and how it feeds into M24 moonshine, again, to set the stage for Anne's talk afterwards. And I mean, the ideas and the results are summarized in our joint papers and preprints here, and then I have a very, very recent small preprint where I also try to give a little bit of a background. So what about the elliptic genus? The elliptic genus, we can motivate the elliptic genus. Another reason why I choose to, or like to talk about it, by one of my most favorite theorems in mathematics, namely the AtteaSinger index theorem. So I'll use that as a motivation, and we'll come back to it several times in this talk. So AtteaSinger is a classical theorem which actually works in quite big generality for any compact-oriented two-dimensional spin manifold and a vector bundle and a Dirac operator associated to it. And this fantastic theorem tells you that you can calculate a topological invariant, the index of this Dirac operator, by means of curvature data, really, by an integral over certain characteristic classes. And all the ingredients here, I'm giving the details down there, all the ingredients can be calculated locally from the geometry of that manifold from curvature data. So it's a really beautiful theorem and a very powerful theorem with a complicated proof, of course. And one, actually, not the first proof, but a very beautiful proof uses the so-called McKean-Singer formula, which is this equality on the right-hand side, which tells you that you can actually calculate the index of this Dirac operator by means of a trace of the heat kernel. So this is a symbolic way of writing the heat kernel. And on first sight, this equation may be confusing because on the right-hand side we seem to have a dependence on t. But that's, of course, precisely the point. One proves that the right-hand side is independent of t, and then it means that in order to calculate the index, I can evaluate the right-hand side at whichever value I like. In physics, we would send 10 to infinity, and we would notice immediately then that all the ingredients, all the contributions to this trace of the heat kernel actually boil down to contributions from the co-kernel and the kernel. So this is how you literally produce the index then. And on the other hand, if you send t to 0, then you have to work much harder in order to see that actually the heat kernel then produces expressions like so. And this was done by Getzler to show that the heat kernel for t close to 0 can be expanded in a way so that you can read off these characteristic classes contributions. So that's the AtteaSinger index theorem, and all these formulas will keep reappearing in the talk. Now, for simplicity, actually, I will, in what follows, simplify the assumptions. I will use Calabi-Yau defaults all the time. I mean, many of the things I'm going to say are working in greater generality, but for the applications that I have in mind, of course, it's sufficient to consider Calabi-Yau defaults. So M will always be a Calabi-Yau default. in this talk. And then you can actually rewrite the AtteaSinger index theorem by using this fact that you're working on a more special manifold than we assumed up here. T then will always denote the holomorphic tangent bundle. We're applying our theorem only to holomorphic vector bundles, and then this index here just happens to be what we call the holomorphic Euler characteristic, and kind of reshuffling the terms in here. Instead of the A roof genus, you obtain the Todd genus, where I'm reminding you of the formula down here. Now, of course, everyone knows examples of applications of this theorem. I mean, the standard topological invariance of your Calabi-Yau manifold can be calculated by means of index theory. You just have to choose your Dirac operator appropriately, this one here. So, for instance, the Euler characteristic is an example. Yeah, you just choose the usual de Rham differential as the Dirac operator, and you can calculate it by means of such an index formula and obtain the precise value of the Euler characteristic, which I can express in terms of the Hodge numbers like so. Or Hutzable signature is another nice example. Where you actually use the same Dirac operator but a different spin structure, use the different Z2 grading to obtain from the very same theorem the expression, the index theory expression for the signature. And again, in terms of Hodge numbers, this is what you get. And then finally, what we call the holomorphic Euler characteristic arises if you insert a trivial vector bundle down there. And I denote this in this kind of sheafy notation by OM. So the holomorphic Euler characteristic arises if you take the index where you only use the holomorphic contributions to the stuff up here. Or, that's equivalent, only the anti-holomorphic contributions. All right, so that's this favorite theorem of mine, the AtteaSinger index theorem, and I claim it is closely related to a discussion of the elliptic genus, and Jeff also mentioned that yesterday already. What's the elliptic genus? Well, very naively one could say the elliptic genus is just a very pretty function in two complex variables, one on the upper half plane and one everywhere on C, which interpolates between these three standard topological invariants. By interpolation, I mean precisely these equations. And by pretty, I mean that it's going to be a weight zero weak Jacobi form whose index depends on the dimension of your manifold. Now, mathematics is, of course, not how you define the elliptic genus. In mathematics, you define the elliptic genus as a ring homomorphism from cobordism classes and manifolds to rings of, well, automorphic functions or Jacobi forms, whichever application you have in mind. And what I'm writing here is, of course, just a much more low highbrow version of precisely that. But for our applications, it's more useful to keep in mind that there's a relation to the AtteaSinger index theorem, and Jeff actually mentioned that yesterday already. We can view the elliptic genus as arising from a regularization of an equivariant index on loop space of M. And that's, of course, very close to our hearts because the loop space of M is just the continuous maps from a circle into M, and that's, of course, one of the gadgets that we need in nonlinear sigma models. Now, I would like to write down an index of a Dirac operator on this space. If I do that, then I'm in trouble because it's an infinite dimensional space, so we don't even know what a Dirac operator is, let alone what its index is. However, and I'll go into more detail a little later, one can introduce an equivariant version and then regularize it. And when doing so, you arrive quite naturally at an expression which I hope you recognize as something which is very, very similar to the expression in the AtteaSinger index theorem. Here, this is precisely the integral we saw on the previous slide. Where, of course, I'm hiding all the difficulties in this bundle EQ minus y. It's not really a bundle. It's a formal power series in Q and y whose coefficients are exterior and symmetric powers in T. And if you've never seen this, then this notation, of course, needs to be digested. So I'll copy it on the blackboard, and you have time to stare at it a little longer. And this will also play some role later on. So we have a prefactor, which is already with a plus sign here. And then we have the exterior powers of the cotangent bundle here. First one I'll copy out separately. And then we have this infinite tensor product. With exterior powers and symmetric powers contributing. And this notation, where we have this lambda or the S with a variable down here, is also explained on the transparency. This is just a convenient way of, again, writing a formal power series with values in holomorphic vector bundles. Lambda xe is just the formal sum where you place the variable x to the p in front of the p's exterior power. And then similarly for the symmetric powers. So now I have a prescription of what this bundle here really is, or this formal power series with values in bundles. The Chern character is just introduced to be a homomorphism, so I'm allowed to pull the sum and the x to the p in front. That's just done by definition. And then I can make sense out of this expression here by pulling all the formal variables in front and then evaluating each coefficient, again, by the AtteaSinger index theorem, where it will give me a holomorphic Euler characteristic of some exterior and symmetric power of S. So the elliptic genus, as you can see here, is very closely related to the AtteaSinger index theorem. In fact, we'll see more of that a little later in the talk. And I already mentioned in the context of the AtteaSinger index theorem that we have a second beautiful formula which can be used in the proof, namely the McKean-Singer formula. And again, we have a similar formula for the elliptic genus, which is just our usual expression of the elliptic genus in terms of conformal field theory data. Because, I mean, this formula has been put on the blackboard several times already over the last few days. HR is the Ramond sector of some conformal field theory, maybe arising from a nonlinear sigma model construction on M. And then this expression, of course, is very reminiscent of a heat kernel, and this is actually how you should read it. A priori, there's no reason why the elliptic genus in conformal field theory should agree with the elliptic genus in geometry. So here, this is actually a theorem. And well, in many cases, you can just check it. Like for K3 surfaces, you can simply check what the function is, what the weak Jacobi form is that you obtain from your K3 theories, and you can check that it agrees with the one that you produce in geometry. But understanding why there should be equality signs here, I think, will be crucial to really understand what's going on with the elliptic genus, also in the context of Mathieu Moonshine. So I'll spend some time explaining to you other people's results which explain why these equations should be true. And that's also paving the way for a point I want to make later on.
What were the conditions on M for this theory?
For which one?
The manifold M.
Well, at the moment, I'm simplifying by saying I'm using Calabi-Yau. You can define the elliptic genus in much more generality, but then you won't necessarily produce a weak Jacobi form. So you break the nice modular invariance. So you can do this. I mean, the elliptic genus can be defined for smooth manifolds, right? I mean, cobordism classes of smooth manifolds. Then in order to write down this expression with Todd, I do need a complex structure. I could go back and write a different integral expression without using complex structure, just use a smooth manifold, yes. And then on the right-hand side here, at least for the argument I'll give, I do need Calabi-Yau. And I'm not sure how to generalize this away from Calabi-Yau, but we'll get to that. And please ask again if it's not clear, because there's a crucial point where we really need Calabi-Yau and all the Calabi-Yau conditions in arguing for this equality here.
I have a historical question.
Oh.
What did Witten do?
Okay, I'll explain a little later. As far as I understand, I mean, maybe I didn't do my research properly, and I'm happy to learn. As far as I understand, Witten gave the argument how to interpret this expression here in terms of an equivariant, a regularized equivariant index. So his papers at least are the ones where I learned this from. And we'll see how to interpret this expression here in terms of something which is really, really close to nonlinear sigma model language. And again, that's going to be crucial in order to understand this whole business behind the elliptic genus. So this is just kind of a motivation to tell you how great the elliptic genus is, and there are already questions now, so there are many things that still need to be understood better, at least I need to understand them better. And for the plan of this talk, indeed, I want to explain in more detail how we arrive at this expression for the elliptic genus as a U1 equivariant loop space index, because this is also paving the way for something that we're all expecting to happen, namely that there's a vertex algebra underlying the elliptic genus, a vertex algebra which can be used in order to, where we take a graded trace and then we produce the elliptic genus. This prediction that comes from Mathieu Moonshine, and I will claim that we already know how to calculate that vertex algebra, and I'll present results by other people who have taught us to do that. And that's what's hidden behind this title as a sigma model interpretation for this expression back there. That'll be crucial. And then, paving the way for Anne's talk, of course, I'm going to specialize then on my favorite Calabi-Yau manifold on the K3 surface, try to summarize what's up with the Mathieu Moonshine ideas there, and try to pave the way for the ideas we have to maybe shed some light on Mathieu Moonshine. And in the final section, I'll summarize some conjectures, some of which are proven and some of which are open, and one of which actually is independent of Moonshine. All right, so back to equivariant indices. As I said, a kind of very low eyebrow motivation for this elliptic genus is to say, well, wouldn't it be nice to have some function that interpolates between these three standard topological invariants? And that's something Hirzebruch could already do in '78. He introduced his Hirzebruch chi-Y genus, which is just a linear combination of our Hodge numbers with this variable yp inserted there, and you see immediately that this already allows you to interpolate between these three indices. We have chi minus 1 here, we have chi plus 1 here, and we have chi 0 there. For later use, it will be useful to rewrite this a little bit, again using AtteaSinger. So from here to here, I'm just inserting the definition of the Hodge number. From here to here, I'm inserting the definition of the holomorphic Euler characteristic for a vector bundle. From here to here, I'm using AtteaSinger to rewrite the holomorphic Euler characteristic in terms of our favorite integral with Todd inserted. And from here to here, I'm just inserting this new notation where lambda sub y t star means the formal power series of these bundles with the prefactors y to the p. And then in the last step, and that's going to be useful when interpreting the U1 equivariant loop space indices later, I'm rewriting this classical index in terms of the data of the so-called splitting principle. So these xj have appeared here, and they come from up there. The splitting principle says that you can write your total Chern class of any vector bundle in terms of a factorized form. Now, if your vector bundle is just the holomorphic tangent bundle, so that has rank D, if this was a direct sum of line bundles, then an expression like this would be completely obvious. Then the xj would be the first Chern classes of the summons, of these line bundle summons. Here's the total Chern class, which is the sum of all the Chern classes of T up to the total degree. And the beauty of the splitting principle is that, or the observation in the splitting principle is the fact that you can use such a factorization globally. So I'm kind of introducing these wannabe first Chern classes of line bundles, because locally, if I restrict T to some sufficiently small neighborhood, of course, the bundle will decompose into a sum of line bundles. That's how you're supposed to interpret the xj here. And this means that all the Chern classes of T can be expressed in terms of polynomials in the xj. And because all these characteristic classes that enter in here can be expressed in terms of Chern classes, it means that I can rewrite this expression under the integral in terms of the xj. Now you have to know your definition of the Todd genus. If you remember on the previous transparency, I had written it. It's the determinant of the curvature of T divided by 1 minus e to the minus curvature, and that's actually the expressions you see here. The product of the xj by this up here is the top Chern class, can be given by the determinant of the curvature, so that's this factor xj, and then the division by 1 minus e to the minus r can be seen here, and the numerator is responsible for that Chern character. I have to stare a little bit on it to check that. So that's Hirzebruch's chi-y genus, which does this interpolation thing very nicely, but of course it's by no means a weak Jacobi form. We have to introduce another form of variable q, and you can do that in a sensible way by means of equivariant indices on loop space. So again, if I just naively go ahead and write down an index of a Dirac operator on this space, I'm in big trouble because it's an infinite dimensional space. However, one can fix this by calculating an equivariant index instead and by regularizing it properly. Equivariance with respect to some nice group actions on this loop space. And the group action we're taking is just S1, so Q is going to be an element of S1. And I want to define an equivariant index on loop space. An equivariant version of a Dirac operator index on loop space where I generalize the Hirzebruch chi-y genus. And Q then is just a group element in S1 or U1, whatever you prefer, and this acts very naturally. It simply acts by rotation on this circle on your string if you want. It just acts by rotation on the string. So here I'm using the mathematical terminology. Q is supposed to be a topological generator of S1. By this I mean it's an element in S1, so it's a rotation if you want, but not just any element. It generates a dense subgroup in S1, so I want non-rational rotational angles here, and that's just in order to get the regularization property. So Q lives in S1, and now I want to write an index theorem, and I want to just brutally generalize, well, the expressions that we know from finite dimensional manifolds. So I'm probably going to produce some product J goes from 1 to D, and I will have to generalize this expression here. So let me copy it first. Okay, to integrate now, I mean, a priori I would have to integrate over this infinite dimensional loop space, and then I'm in trouble. But luckily, there is a generalization or a version of the index theorem due to AtteaSinger, which teaches you how to calculate equivariant indices, and from the start it tells you that instead of integrating in this index theorem, instead of integrating over the entire manifold, the integral will localize on the fixed point locus. So instead of integrating over Lm, I need to integrate over the fixed points under the S1 action. Now, such a circle will be invariant under rotation of the circle if and only if it has shrunken to a point. So really, the fixed point set here is just the manifold itself given by the constant loops. So the integral will not be an integral over Lm, but it will be an integral over M. All right, now I have to introduce this equivariant version of the index. I didn't even tell you how to do this yet. Well, you're all familiar with twisting elliptic genera. So you have the definition of something in terms of a trace, and instead of using just a bare trace, you also insert some group element. That's the twisting here. And the same thing happens with the equivariant index. We agreed that we have the McKean-Singer formula, which allows you to express the index in terms of a trace over a heat operator. And instead of just taking that, you also insert Q. So that's what's happening here in the definition of the equivariant index. So on the right-hand side, I just have to also take into account the action of Q. And in order to do that, we need to take a look at the tangent space. I don't want to go into too much detail here. You simply prove that the tangent space in such a constant loop for the loop space is actually the loop space of the tangent space. It's kind of obvious. I'm trying to put a first-order deformation to a constant loop. What I need to do is use a loop in the tangent space. So that's this equation here. And then for such loops, you perform a Fourier analysis. You write the loop in terms of a Fourier sum, and you get contributions from all the Fourier components, and that's what's happening here. You have infinitely many copies of your tangent space. And on the nth copy, that's the crucial point now, on the nth copy, your generator of S1 will act by q to the n. So this notation is just a mnemonic notation. Qn TPM is TPM, but I'm remembering in the notation how q acts, namely with eigenvalue q to the n. And that, with a little more work, tells you that in here, I have to keep track of the q to the n inserted into your trace if you want. Oh, it always falls. I'm too slow. It falls asleep. All right, so this would be a good guess. I'm hiding, of course, a lot of details. In particular here, the denominator is a little bit harder to argue for, but this is more or less what it is. This would be a good guess for writing down an equivariant index on loop space for a Dirac operator. Unfortunately, this doesn't converge, so you have to regularize. But the regularization now, once you've written that, is actually very, very easy, and I've written for you the correct expression on the transparency. The regularization is very straightforward because essentially all you do is you reorder this product and then you massage some of the factors a little bit. So this infinite product, I've actually separated the n equal to 0 contribution here. That's the classical contribution, which we already knew up here. Then first come the contributions with positive n. So I've just copied out. I hope I've copied out what's written here. And then back here, these are the contributions with negative n, but I've done a little bit of massaging. I've renamed n into minus n, and then I've multiplied the whole thing, numerator and denominator, by this expression q to the n times y to the minus 1 e to the xj to bring it into this form to make everything converge. And that works very nicely because this quotient here, numerator and denominator, looks so similar. However, in the denominator, of course, there's no contribution of y. So the mistake I've been making here is a contribution of y, a factor of y, for every n. And those infinitely many factors of y are actually summarized back here. This is where the regularization happens, and it's a very straightforward regularization. It's simply zeta function regularization. And now you may know that zeta of 0 is minus 1/2. So these factors here are actually responsible for the prefactor that we already have up there. Remember, I have a little sign flip here. So this is the expression for the elliptic genus as it arises from this idea of regularization of a loop space index. And now if you stare at this and if you remember your splitting principle, it's not very difficult to ensure yourself that this is actually the expression that you get when you take the Chern character of this formal bundle, of this formal power series with values in bundles. Because right here in front, you see the traditional contributions together with the Todd genus. So this we already talked about. And then here, the exterior powers are taken care of in the numerator with the Chern character producing precisely these values, and the symmetric powers being produced in the denominator. So from here to here, it's again a little bit staring on the formula and getting used to the notation. So this is how one could have guessed what the elliptic genus could look like, but then of course it's hard work to show that you have produced something well-defined and something with all the properties that you wanted. So now this is the theorem that this is not just a formal power series in q and y, but actually it's a well-defined function for tau in the upper half plane and z in the complex numbers, and that it has all the nice transformation properties which we know and love, at least for Calabi-Yau folds. It produces a weak Jacobi form of weight 0 and index d-half. And luckily I don't have to explain what these words mean because Samir has explained it to us already.
I just missed the point where you use the fact that it's a Calabi-Yau.
Right now, to show that you have the transformation properties, you need the Calabi-Yau property. And all the derivation of this expression here, I didn't use it, and actually I don't need it. So indeed, this expression holds in much more generality, and many things that I'm going to explain hold in much more generality. Just for simplicity, today I'm assuming Calabi-Yau, because that's where I'm aiming, and I don't have to kind of sort new assumptions in every theorem that I'm stating. All right. So this is the elliptic genus, which definitely plays center stage when we consider Mathieu moonshine and many other interesting things that we've heard about already this week. So some of the predictions in Mathieu moonshine indicate that there actually should be a vertex algebra governing the elliptic genus. And I would now like to convince you of the fact that such a vertex algebra has been constructed already. It's maybe not so much appreciated in the physics community because the papers are a little bit difficult to read maybe. But the ideas that enter here are very, very natural from a physics point of view, and I'm going to try to convince you of that. So I'm claiming we should use the chiraldrom complex. So that's something which on first sight looks very fancy, but it's really, I mean, literally copying ideas that come from string theory, writing down BC beta gamma systems locally and then patching them together so that they produce something sensible, something mathematically sensible on our manifold. And again, the construction doesn't only work for Calabi-Yau manifolds, but this is the case I'm going to focus on here. So what's this chiraldrom complex? You construct what I call a sheaf of vertex algebra. And first of all, this means that for holomorphic coordinate neighborhoods, you attach vertex algebras, quite natural ones, namely BC beta gamma systems, in fact, d copies of those. So we have d copies of a quadruplet of fields, which you can geometrically interpret, and that's going to be helpful in a second. The phi's will correspond to the holomorphic coordinates. The p's will correspond to the holomorphic tangent vector fields. The xi's will correspond to the holomorphic first differentials. And the rhos will correspond to, if you want, the duals of these guys. And the fields here, these are just, as I said, BC beta gamma systems. So here are the bosonic fields. Phi and p are the bosonic fields. Psi and rho are the fermionic fields, and these want to be free bosons, these want to be free fermions, but in a topological situation, so the weights are actually 0 and 1 here, as you can see, read off from the exponents, and again 0 and 1. And here are the familiar anti-commutator relations for the modes. And these fields live on some Fock space, which you just easily construct from a vacuum. As usual, the negative modes are the creators. The positive modes are the annihilators, as I'm noting down here. And you only have to be careful with the zero modes. The zero modes of the weight 0 fields act non-trivially, while the zero modes of the weight 1 fields act trivially. And that's encoded down here. And now, stare at that expression back there. You'll notice a very, very direct similarity. This is really just, if you want, a graded version of the Fock space here. Because, well, right in front, here we have the DZJ. So these are the zero modes. These capture the zero modes. This bundle here captures the zero modes of the psi j. Here the exterior powers of T star and D capture the creators of the fermionic field. So here we have the psi j minus n and the rho j minus n. This will have to be, well, back here, of course, we have the tangent space. So we will have the rho j, no, pj minus n. And then the only one who's left is phi j. Sorry, every time I speak about this, I use different notation, so I don't remember who I called what. So this is what happens locally, and we're all familiar with it from string theory. It's just the old BC beta gamma system idea, and now we make a sheaf out of it by gluing the coordinate patches appropriately. And this is the idea in the Malikov-Schechtman-Weintraub paper, that you do something very, very natural, because we know how these geometric quantities transform under coordinate transformations. I know what to do with the coordinates. I know what to do then with the tangent vectors and with the first differentials and with this stuff back here. We kind of have natural prescriptions of how these fields transform under coordinate change. So how to patch them together on the entire manifold is completely determined by the geometric interpretation of these fields here. And that's what they do, and they show that with these transformation rules that they give, it's a lengthy calculation. Once you perform these transformations on the fields, that actually after the transformation again you have a BC beta gamma system, so everything is compatible. So there's something that you need to check here, but it had to work because we've been doing this in string theory forever. So indeed, you can construct a sheaf of vertex algebras on M by this very, very natural idea of just locally using BC beta gamma systems, the copies of that. What is Y? Well, it's kind of a formal variable which determines, which at the end of the day will determine charge. Yes, but I haven't told you that there's charge here yet. I haven't told you that there's a U1 current yet, but that's going to be next. But it kind of counts. It counts the contributions from the phi's and the psi's. So we're going to give phi charge +1 and psi charge -1, and then it keeps track of the charge. And Q keeps track of the weight. But both these notions don't yet make sense in the context of the chiraldrom complex. Of course, for you it makes sense because you're familiar with the BC beta gamma systems. So yeah, so everything completely natural, and as you would expect it, really.
The chiraldrom complex depends on the complex structure.
That's right, and nothing else. And I'll come back to that later. Yes, it depends on the complex structure. As we can see, I mean, the dependence might drop out. But here we're actually using the complex structure. In the transformation rules for these fields, we're using the complex structure because literally we're using the holomorphic coordinates and holomorphic coordinate changes. So this is where it comes in, and that's important, yes.
So when you say BC beta gamma, do you mean like free bosons and fermions, or is there some slope there? And what's the central charge of the BC beta gamma?
Of the total system is 0.
No, but just of BC.
No, we have the bosons here and the fermions there.
So it's just bosons are central charge.
Okay. The free bosons, if you just restrict to the free bosons, then you will get central charge D.
They're really free.
Yeah. That's right.
So I should really just think of some little small patch of the tangent space.
Exactly.
And the free string theory.
Exactly.
The free CFT of the string theory will do
Exactly.
small patch of the tangent space.
Exactly.
Okay.
Exactly.
Twisted.
Yes, it is topological to twisted. Yeah, that's why my fermions have integral modes only. Yes, indeed. And that'll be crucial in a second as well. Yeah. Okay, so this way you construct something that is mathematically sensible, and of course we don't expect these nice BC beta gamma fields to be globally well defined. Our coordinates were never, our coordinate vector fields were never. But now, again, not surprising for string theorists, but the crucial observation in this paper is that actually from these ingredients you can construct fields that are globally well defined. So if you hit these contributions here in the normal ordered products with your coordinate transformations, then it's a hell of a calculation to check that these expressions are actually invariant. So the fields that we're defining here, and really not a very surprising way from a string theory point of view, are globally well defined, and they give you a topological n equal to superconformal algebra. And yes, indeed, it's topological, as was pointed out, and that will be crucial in a minute. Well, okay, I mean, hard is, of course, I mean, it's 4 pages in the paper. It's just keeping track of the indices. It's just keeping track of the, and the complication is also that there are many typos in this paper. So, I mean, there's nothing deep in there. You just go through the whole calculation, and and since you know that this has to work, somehow there's a treat that's waiting for you and that you know that you're going to get. So there's no deep idea. There's no deep idea. You hit this with your coordinate transformations, you go through the calculation, and then it's a couple of pages long. I mean, all of you have done harder calculations, of course, in your life. But it's not, I mean, it's not that I can just kind of point my finger on it and say it's obviously going to work.
Where do you put in the data that you're maybe on T4 or K3?
When I'm going, in 10 minutes? So at the moment, I'm only using the complex structure. I'm only using the complex structure, and then as a result of these papers, you see more of the structure, of course. At the moment, I'm just using the complex structure, and in some sense already globally, because I'm covering my manifold with the open charts, and then I should somehow have encoded, for instance, the properties of the tangent bundle, and I have. Now, it's easy to check, I mean, compared to that calculation, it's easy to check that the graded sum actually should give the elliptic genus, because, I mean, I think I've convinced you of it already, because over here we literally have the model for the Fock space. And also this fact that we have packaged it together for local data is hidden in here, because we're always using these infinite products with the xj in there, and the xj actually take care of the fact of localizing your contributions from the Chern classes. So this you can check immediately. You have a bigraded Euler characteristic, by which I mean that you obtain the elliptic genus now as a supertrace over the chiraldrom complex of an operator y to the j naught, q to the l naught top. However, you have to shift here by just something that makes the whole thing modular invariant, and that's our favorite prefactor, y to the minus d half, which you put in by hand. So that's the operator you take the supertrace of. And then with these ideas here, you produce precisely the expression for the elliptic genus that we already know. So already now I've produced something vertex algebra-like underlying the elliptic genus, but it's not really that good, because it's a sheaf of vertex algebras. We're not really normally working with sheaves of vertex algebras here. But now the big observation in these papers and then clarifications in Borisov and Lipkuba is the fact that actually we do have a vertex algebra associated to this whole thing. You have to take the cohomology, they say. You have to take the sheaf cohomology for this sheaf, of course in the elliptic genus by standard arguments and cancellation theory if you want. I can replace the chiraldrom complex by its cohomology. I mean, you have the usual cancellations of contributions here, so that I'm allowed to do that. And this is a better object than the chiraldrom complex, because on this object, they claim you actually produce an honest topological n equal 2 superconformal vertex algebra. These fields descend to the cohomology, and then this is a vector space, a graded vector space whose graded trace we already know. And this vector space has an associated vertex algebra. It's not easy to calculate it, but together with Scott Carnan, we've done some examples already, so we kind of now, I feel I have a bit of a better intuition of what this vertex algebra looks like. And indeed, probably it depends on the complex structure moduli. We don't quite see this yet, but it's not a topological invariant, really, the vertex algebra.
What type of examples?
Well, we're, of course, looking at tori and their orbifolds.
I recall there's a paper by Kapustin that says something like...
Yes, of course. I have to cite Kapustin now, because still we haven't produced really the object that we expect from string theory. Because in string theory, when we look at the definition of the conformal field theoretic elliptic genus, it's again down here. We actually know how to guess, how to write down a vertex algebra, or at least the fields or the states that contribute to the elliptic genus here. We have to perform a topological twist on the right-hand side. So we're working in Witten's half-twisted model, and we're restricting to the Ramond sector. But what we get then will definitely depend on all the moduli. while the chiraldrom complex never saw the choice of a metric. So here it's only the complex structure that is entering. So somehow this can't yet be on the nose the structure that we obtain from our conformal field theories. And Kapustin now argues that what you need to do in order to translate from one language into the other is really perform a large volume limit. And again, there are a few technical details. I told you that the cohomology that I'm writing here is check cohomology. It's not so easy to work with check cohomology, but in mathematics we know that we can replace check cohomology by many other more convenient cohomologies, and Kapustin as a first step uses this thing that he calls Dolbeault cohomology, and it's much closer to the objects that we want to produce. We just introduce by hand the holomorphic, the anti-holomorphic partners of our holomorphic coordinate fields and the dzj bar. And one can show that then cohomology with respect to this exterior derivative here is the same as the check cohomology. So instead of what I wrote here, I can write this expression where I use the Dolbeault cohomology. And then he argues that in a large volume limit of the BRST cohomology of Witten's half-twisted sigma model, you literally reproduce this guy over there. So that explains why the geometric elliptic genus, which I've been discussing so far and which we were modeling by means of the chiraldrom complex, why the geometric elliptic genus has a chance to agree with the conformal field theoretic elliptic genus, because now again reading from right to left here, this is our traditional definition of the conformal field theoretic elliptic genus. We all know that, again, by these usual cancellation arguments, I'm allowed to replace HR by the BRST cohomology here. Now, I should write a large volume limit in front of this. However, of course, we know that this whole expression is an invariant on moduli space, so I don't care which volume you've been looking at. I can send the volume to infinity. And then I have to adjust all these shifts here, but that's nothing but a spectral flow, and everything actually falls into place then. Now, clearly, with the Ramon sector, I'm in bad shape to write down a vertex algebra, so we needed to go to the Neuve-Schwarz sector anyway to find an underlying vertex algebra. So this is where it's the only paper in the literature where I know where we really argue piece by piece why the elliptic genus calculated in geometry should agree with the conformal field theoretic elliptic genus. And there's a bit of a mess in between, because we have to perform this topological half-twist, and we have to perform the large volume limit to really match the underlying vertex algebras. So let me note that down. Need the topological half-twist. And the large volume limit. So all this holds for all the Calabi-Yau manifolds. I wanted to head for K3, so let me briefly remind you of some of the K3 specialities that we then find. Now, of course, the elliptic genus of K3, you've seen this weak Jacobi form of weight 0 and index 1 several times already. I don't have to say much more about it. I would like to remind you of the fact that I can define a K3 surface simply by saying it's a Calabi-Yau twofold, and it's not the torus. Because there are only two types of Calabi-Yau manifolds, and in fact this dichotomy, to prove this dichotomy, one can use as a first step the elliptic genus. We all know, we've already learned, that the space of weak Jacobi forms of this weight and index is one-dimensional. Now you have to use some high eyebrow mathematics to argue that the only sensible collections of these topological data that you can read off from the elliptic genus are actually the ones where you either have vanishing elliptic genus or precisely this one. Use some index theory arguments again to do that. And then another difficult mathematical argument will show that when the elliptic genus vanishes, and you're in the Calabi-Yau setting, then you're working on a torus. And when the elliptic genus is this, and you're in the Calabi-Yau setting, then you've produced a K3 surface, and in fact all K3 surfaces can be deformed into one another. Very, very difficult mathematical statement, but true. So there's a dichotomy for the Calabi-Yau twofolds, which can be linked to the elliptic genus. And we have a similar situation in conformal field theory, where we just have to be careful to state our assumptions properly. We're working with n equal 2 superconformal field theories with the right center charges to work with Calabi-Yau two-folds at the end of the day. In addition, we have to assume space-time supersymmetry because I need the spectral flow. I already used it in my argument. And we also need integral U1 charges, so in some sense we need more than one spectral flow operator that are compatible with one another. And from these assumptions, it's not terribly hard to prove that one automatically has n equal 4 supersymmetry. That's the analog in geometry of the fact that our Calabi-Yau two-folds all are hyperkähler. And also one can show that the elliptic genus will either vanish or agree with this function here. So that's again a little bit of a tricky argument where you show that no other multiples of the elliptic genus actually make sense. So again, you have a dichotomy. One can also prove that with vanishing elliptic genus, one automatically has a toroidal conformal field theory in the sense that most of you are familiar with. So at least from a mathematician's point of view, it's natural just simply to define all the other theories which obey these assumptions and which are not toroidal as the K3 theories. This means that we can't exclude components of the moduli space which might not be nonlinear sigma models. And of course, in all the arguments we're using here, we're using ideas from nonlinear sigma models. And that's the component I'm going to restrict to. But the definition for K3 theories doesn't make that distinction. Now, off to Mathieu Moonshine. You've seen this argument already in Jeff's talk in not that much detail, but we've learned that when we decompose the elliptic genus into irreducible n equal 4 characters, some interesting things happen. And we do that because we know that the geometric elliptic genus agrees with the K3, with the conformal field theory elliptic genus. On the conformal field theory, we have n equal 4 supersymmetry, so this partial trace of our theory should allow a decomposition like that. And again, we heard that yesterday already. There are 3 types of irreducible representations. And the notation needs a bit of getting used to here because we're working in the Ramond sector for the definition of the elliptic genus. These irreducible representations live in the Ramond sector. However, the notations are supposed to remind you of the properties in the Neveu-Schwarz sector after spectral flow. Because this first massless type of representation with Witten index -2 flows to the representation in the Neveu-Schwarz sector, which contains the vacuum. So H is equal to 0 there in the Neveu-Schwarz sector. Here, this massless matter flows to the fields in the chiral anti-chiral ring. And HH flows to fields where H is just the conformal dimension, conformal weight of the ground states. And that's, for me...
Sorry, does the normalization of the thing follows from uniqueness of the vacuum, essentially, or is it...
Where are you? Here?
Of the elliptic genus. There is one representation which flows to the vacuum to spectral flow. Is enough to normalize the elliptic genus? No.
Yes.
Yes.
Yes, it's enough, but I didn't say that yet. So far I only listed the possible representations. So that's in the classification by Taormina and Iguchi and Taormina. So far I've only listed the representations, and I've used this notation to make it easier to read this ansatz, because now I'm making an ansatz, so I should allow left and right contributions from these 3 ingredients. But you noticed immediately that I didn't list all of them. I only listed a single component, H0 tensor H0 bar, and that's because under spectral flow, this flows to the representation which contains the vacuum, and there should be a unique one. So we have a factor 1 here. Also, we have a factor 20 here, and we don't have any mixed terms between h0 and h1/2, and that's because I already know that I want to work with a K3 theory, so I need to produce the correct elliptic genus, and that's sufficient to fix this first part of the ansatz. And in the second part of the ansatz, again, I'm using this knowledge that we have to spectroflow to well-defined fields, because a priori I could have mixed terms between vacuum representations on the right-hand side and arbitrary massive representations. But here I'm restricting to integral n, and that's because after spectroflow I need well-defined fields. And similarly down here. And when I have that, I can read off the decomposition of the elliptic genus. So now we have an ansatz for the Ramon sector, and inserting the definition of the elliptic genus, I will produce the elliptic genus again as a sum over all these contributions with the character on the left and the Witten index on the right. So then you see that we get the familiar form of the decomposition of the elliptic genus, where the h0 bar here produces the prefactor -2. Here we get prefactors 1 multiplied by 20. Then from here we get fn multiplied by -2, because that's the Witten index over here. Here we get gn multiplied by 1, because that's the Witten index here. And everybody else doesn't contribute, because the Witten index of these massive representations actually vanishes. So these guys don't contribute. So I obtain this expression here, where in particular our little function e, which is our favorite in Mathieu Moonshine, has this expansion. And from this you can already read that you should expect the coefficients to be non-negative. That's why I went into this detail of explaining the ansatz. From this you can already read the expectations that the coefficients should be non-negative, because fn after spectral flow counts holomorphic fields that are not contained in the vacuum representation. Now look at this on the moduli space. While deforming your theory on the moduli space, the fn, gn, and k, they will change dramatically. Fn, again, counts holomorphic fields, but at fixed value n, at a generic point of the moduli space, I don't expect to find additional holomorphic fields. So if I look at fixed n and sit myself at a generic point in the moduli space, I'm expecting fn to vanish. And that means that the nth coefficient here at a generic point is simply reduces to gn, but gn is a non-negative multiplicity, so the prefactor here should be non-negative. So from this decomposition and from this ansatz, you can expect that the coefficients here should be non-negative. It was proved by Eguchi and Higami a couple of years ago, of course, in the context of Mathieu Moonshine, where we have learned much more interesting properties for these coefficients. So originally, as a conjecture or as an observation, they observed that these numbers reproduce dimensions of representations of the Mathieu group M24. That's an empty statement, because one could just have multiple trivial representations. Well, this is maybe not the best way of phrasing this observation cleanly, but it has been proved, and thereby also been made into a proper mathematical statement by Terry Gannon, using all the previous work by many people, and some of them in the audience, actually.
So how proof this thing?
Which one?
In the previous transcript, yeah.
How do you prove that this is non-negative?
Yeah, how would proof go very quickly? Based on Rademacher,
Yes.
I see.
So it's actually analytic proof where you determine the growth behavior of the coefficients. Yeah.
Just as a comment, I have another proof of this which does not rely on, you can just algebraically prove that these things are positive. I can show this to you.
I would be very interested, yes. Yeah. That's interesting.
It's based on one of these formulas I wrote for the H2 function using some functions called F2 and E2.
I see. Okay, that's interesting. So So at least this expectation that there are no generic holomorphic fields is not proved by this. But of course, because the expectation of the positivity was linked to the expectation that there are no generic holomorphic fields other than the ones contained in the vacuum representation, there's a bit of evidence in favor of that conjecture, of that expectation.
In the previous slide, you said without trivial summaries. You mean not one? Or what exactly?
Yeah, not one.
Not one.
Not one, because I can, of course, construct the
Ones, yeah.
using ones. I can make this statement trivial, but that's not what I meant.
Does appear sometime.
At the beginning, yes.
Not
Also later. Okay.
You mean without exclusively?
Yes. Yes.
There were some things.
Well, I should put that away anyway, because this is not. I mean, this was not supposed to be the mathematical formulation.
But
because
large enough is not never exclusive, right? You can always, if it's a large enough number, you can always build things without one.
No.
I think the identity representation often occurs,
Often,
Yes.
yeah.
but it just doesn't. I'm
You
not
don't
sure
use it
that's-
exclusively. But anyway, this is the statement.
Yeah.
Or this is the statement now rephrased with observations that I explained earlier by using Kapustin's results, who says that really we're looking actually with the vertex algebra that governs the elliptic genus, we should be looking at the large volume limit of the BRST cohomology of the half-twisted model here. And then this can be identified, well, with some of these ingredients from n equal 4 superconformal representations, and the multiplicity spaces, and that's of course the important thing here, the multiplicity spaces bear representations of M24, and everything is compatible with twisting the elliptic genera. I don't want to go into detail here with making this precise because that's other people's
I'm
duty.
going to point you anyway. Shouldn't the 2Rn be Rn plus Rn bar? I mean,
Yeah.
representation plus its complex conjugate.
Yes.
rather than
Yes.
plus-
Yes. Yes. All right, but we still don't, I mean, this has been proved as a beautiful result and beautiful contributions to the result, but we have no idea why M24 comes into the picture. The most natural idea one could have, that Jeff already commented on yesterday, would be that maybe there's some K3 theory which has M24 as its symmetry group, but Gabardia, Hohenegger and Volpato proved that that is not the case. There is no conformal field theory on K3 that has M24 as its symmetry group. Actually, sometimes the symmetry groups are not even subgroups of M24, so the symmetry groups of conformal field theories seem not to give the answer here.
So I didn't ask this to Jeff yesterday, but why does this kill any hope of getting M24 out of K3? I mean,
For me, I mean, thank you. It doesn't kill that hope at all.
because the observation doesn't imply a symmetry for the full conformal field.
Exactly. And that's exactly the point we're trying to make. And I already put a mark here where I want to make that point. Well, I don't think K3 is out of the game at all, because there's this beautiful classical theorem by Mukai, which says that actually the symmetry groups, the geometric symmetry groups of K3 surfaces, are always subgroups of M24. And when I say geometric symmetry group, I mean compatibility with the hyperkähler structure, and Anne is going to go into more detail to explain what this really means.
Yeah, apart from the theory that you mentioned, there is this much more easy argument about this M24 action, that there is this 20. Which is annoying. That's much more. It's more immediate.
Well, that's a virtual representation. I mean, that you can interpret in terms of virtual
yes,
representations.
but that's a bit problematic. I mean, it's not easy to build a CFT which has these, but maybe.
True, but I mean, I carefully didn't even write the representations here, although in terms of virtual representations, you can write factors here. But I mean, this is the massless sector. It's a little bit different anyway. So, I mean, we're focusing on the massive sector at the moment.
I mean, you can expect that there is a virtual representation because it's an index.
Mm-hmm.
It's nothing crazy, but it's not. It's not easy to pick to build a thing, have a theory which has a non-vanishing elliptic genus, and has this negative signs there, because you would expect this.
That's right.
1/2 zero fields, and this looks like a toroidal theory. So okay, yeah.
Yeah, the 20 would be another problem. Yes,
yeah,
indeed.
Yeah. So this is quite strong to me. This is quite a strong problem. But
I don't know why you dislike virtual representation so much. So I mean, I don't know why virtual representation should be such a bad thing.
No, it's not a problem with virtual representations. This particular one.
This particular one.
That I mean, if there are higher massive, I think it's kind of easier. But this particular there means that it has specific fields, right? So then.
And one doesn't see them in any construction that we know.
Well, anyway, we all agree that there's no K3 theory with M24 symmetry. I mean, it's, you have many pieces of evidence for that.
Does it make sense of that identity which lets you write this, trade this -280 into some massive, then you write it in a different way, writing it as 24 plus some changes there.
Also true, and then you have 24 is 23 plus 1, so in a way. Whatever, but I'm not going to defend, I mean, because it's simply wrong. I mean,
It is quite general. It's not that you, I mean, it might be a wrong argument, but the difficulty is beyond the fact that the CFTs that we know behave like that.
however, the geometric symmetries behave very well. The geometric symmetries behave very well because the geometric symmetry groups definitely are subgroups of M24. However, by size, of course, they're way off from what we want to get. And this has encouraged Anne and me to believe in this idea that you can just surf moduli space and pick up small symmetry groups from all over the moduli space and then combine them to bigger symmetry groups. And this idea may sound a little crazy at the beginning, but Anne, I hope, will convince you that we have some evidence in favor of it, and I'll also briefly comment on that on the next slide. No, what was that? This is true, indeed, but we'll come back to that. G is, well, but M23 is a subgroup of M24. There's nothing wrong here. Indeed, G is a subgroup of one of 11 subgroups of M23, and the biggest one has this size. So this is a bit elliptic, I agree, but we have something to say about that. And I think Anne will go into detail there. But yeah, as you say, I mean, maybe we're not supposed to be looking at symmetry groups of conformal field series, but kind of only symmetry groups of restricted parts of these CFT. Why would it be the geometric symmetry groups? And I think we have evidence for expecting that from this construction that I've been trying to explain to you. Because if we want a topological half twist, we have to choose a U1 current. And that's part of choosing a geometric interpretation. If we want to perform a large volume limit, I have to know in which direction to walk to get large volume. So really, this construction of Kapustin, etc., makes sense if you have chosen a geometric interpretation. So why not restrict to symmetry groups that respect that choice? So I don't know, this is not a mathematical proof, but this is for us part of the motivation of why we're not so worried about restricting to these small groups, as long as we're allowed to surf through moduli space and pick them up from all over the place.
So just to clarify that idea, the idea is still that on the BPS states, the symmetry should act everywhere.
On the vector space, but it won't respect the vertex algebra structure that is globally existent, and even the vertex algebra that we get from the chiraldrom complex, from this cohomology of the chiraldrom complex, most probably depends on the complex structure moduli. So even there, we don't have a single vertex algebra attached to K3 as a topological invariant. But at every place at every point on the moduli space, we'll have a different prescription of what the OPE is supposed to be, and M24 might not respect that. Not all of M24, but certainly we expect that the geometric symmetry groups in some geometric interpretation will respect that OPE.
Is there a precise definition of what the large volume limit is? Because
there's work by Morrison about that. I mean, in the paper by Kapustin, you just kind of, you extract part of the Lagrangian and to show that that doesn't contribute then in a large volume limit.
The volume of the K3 going to infinity, but keeping the volume of various 2 cycles fixed.
No, that's not allowed. That's not allowed in what we normally in mathematics call a large volume limit. You kind of want to make all radii big.
So it kills all rotating syndon effects.
There's a very nice paper by Morrison, I don't know, maybe in the 90s, mid-90s, where And also Mark Ross and these people in mathematics have thought about how to define large volume limits mathematically.
And our values boundary components to SO420, right?
Say again?
In modernized space is SO420.
Yeah.
And there are various boundary components. I mean, there are various in equivalent to another.
Yeah, you first have to choose your direction. Exactly. So you have to choose geometric interpretation. Yes, it's the discrete choice. I mean, choosing geometric interpretations, I didn't include this in this talk, but amounts actually to an infinite but discrete choice, indeed, of certain.
It's also quoted by SO20 co-formula Z. So if you include T-duality, all those dualities, is there? I think even then there are several different kind of cusps or something. Already for SO2 and two kinds.
Okay, so we think that we can surf moduli space and pick up small symmetry groups, and the way this is supposed to work is that we take this identification and we view it as an equivalence of representations of our geometric symmetry groups, different one at every point of the moduli space. And this right-hand side remains constant, so as you move through moduli space, the group changes and you can collect the group actions from various points in the moduli space on the right-hand side. And there's much more to say about that to make this precise, this idea, but Anne is going to go into more detail there.
So the R half is supposed to be a singlet, M24 singlet.
Well, this is now a 20-dimensional vector space. And when I only use the small symmetry groups, I have no trouble in having them act on this 20-dimensional vector space. So then we have the representations that we need. So as soon as I restrict to the small symmetry groups and I only force this to be an equivalence of the small representations, there's no problem with the 20 here.
Yeah, it has to work that way.
Exactly. Yeah, exactly.
So it seems like the right-hand side collects vector spaces. But to say that it's a symmetry group, don't you also have to say how to multiply elements at different points?
Indeed, and that's, I mean, there you have to say much more. I mean, you have to say which structure. I mean, the basic idea is that we have an integral structure in here. This is cohomology, really. We have an integral cohomology sitting in here. And it kind of remembers, and it also tells you at which point in the moduli space you are. So the surfing idea implies that you can move a moduli space while kind of keeping your compass on, while remembering where the integral lattice was sitting, and the integral lattice really carries the action of your symmetry groups. So as long as I know where the integral lattice is sitting, then I know how the symmetry group will act. So that's kind of the basic idea underlying the fact that you can move through moduli space and pick up your various symmetry groups from different points. But again, that's Anne's duty to explain that better. And I just to maybe raise hope. We have some evidence here. We have some evidence that this idea might work because we've reproduced the first representation here. Yeah, indeed. I mean, we've produced R1, and the other one is R1 bar. Indeed, you're right. As the common representation of all the symmetry groups of Kummer K3s. And I mean, again, the biggest group that you can get here at any point in the moduli space has order 960. But if we play our surfing game, then we can show that we can produce a much, much larger group, this one here, which is a maximal subgroup of M24 already. And okay, so we produce a big group, and it's still a subgroup of M24. That's good news, because otherwise this conjecture is dead. But even better, we can very, very explicitly calculate the representation of this group that we get on R1, because R1 can now be produced as a space of states that all these Kummer K3s share. And we check what this representation is, and we actually find that it reproduces the restriction of an irreducible 45-dimensional representation of M24 of this group. So this is really a trace of M24 because it's not, I mean, we just on the nose calculate what kind of representation we get on these states because we know how the symmetries act in the conformal field theory. And then we compare with the irreducible representation of M24, and we see that's exactly the one predicted by our conjecture, because our conjecture says we should consider the representation of the subgroup here that we've produced that comes from restricting the big representation. And crucially, this is not a subgroup of M23, indeed. Okay, I have almost no time, but I would like to tell you about yet another conjecture, and I not need much time to explain this conjecture, which is not proved yet. Probably it's easy to prove, but I haven't managed to prove it yet. And well, it's motivated by the observation that, well, okay, here we have evidence. Of course, next we have to consider R2, R3, R4, and we'll work infinitely long in order to prove our conjecture, and that's not really sensible. Also, we don't have M24 yet, of course. I mean, there's still a difference here. So this is good for collecting evidence, but maybe not for proving our conjecture. And we don't really know yet how to go about doing this in general, but maybe we should step back and use the ideas that I tried to defend at the beginning of this talk, that really the properties of the elliptic genus and geometric properties of the elliptic genus should be fundamental to understand Mathieu moonshine, at least in the K3 setting. Notice or recall, we interpreted the geometric elliptic genus in terms of this AtteaSinger-like expression. Then we got encouraged by the fact that we have some arguments why this geometric elliptic genus agrees with the conformal field theoretic elliptic genus. And in conformal field theory, we expect to have this decomposition into n=4 characters. But from here to here, something crucial has happened. We've mixed geometry and conformal field theory, and in geometry, we have no motivation whatsoever to write down this decomposition. We don't know what it means to write down the decomposition into n=4 irreducible characters. On the other hand, on the encouraging side of the story, we've been quite successful for the elliptic genus to just generalize the standard index theoretical things to the setting of the elliptic genus. We have this nice AtteaSinger-like expression. We have the McKean-Singer formula, which works. Maybe also the analog of a local index theorem works. So maybe I'm allowed to leave away the integrals here. So what I expect to happen is that this decomposition into n=4 bits, irreducible n=4 bits, already happens on the level of this bundle here. So that we will be able to rewrite this formal power series of bundles with formal variables q and y, and the coefficients are holomorphic vector bundles, that we're going to be able to reproduce an n=4 structure already here in the bundle. And of course, I know what the leading order terms have to be. It has to be the trivial bundle here and the holomorphic tangent bundle here. From this bundle to the elliptic genus, I have to calculate the holomorphic Euler characteristic. I have to throw this integral and the term character over this. We already know that the holomorphic Euler characteristic of K3 is 2, so you produce the prefactor 2 here. Here, the holomorphic Euler characteristic of that bundle is -20, so this is okay. And then the holomorphic Euler characteristic of these polynomials in T, which I expect to exist, will produce as their holomorphic Euler characteristic precisely our favorite coefficients in Mathieu moonshine. So the dimension of our representation producing these prefactors here will be given by the holomorphic Euler characteristic of these bundles. If true, then that's actually a step towards proving our conjecture, because we, of course, have a natural action of all the geometric symmetry groups on T and thereby on these polynomials. Then one would have to show that everything is compatible with projecting down to these representations, but then actually we would have one step towards understanding why our conjecture maybe works. It's probably not even hard to prove this, if only we could prove that there is n=4 supersymmetry in our chiraldrom complex. And there are papers which seem to indicate that, but there are certain mismatches that I don't yet understand, so I'm not going to claim that I know how to prove this. But I do expect that, well, if correct, it's not going to be too difficult to prove this conjecture. And I like the conjecture because I can show it to my mathematics friends without scaring them away with conformal field theory, because notice I can formulate this decomposition without even telling them about conformal field theory. They'll have to swallow the form of these n=4 characters, but that's all I need to put in there. All right, so I'm already out of time, so I apologize for that, and I thank you for your attention.
What's the difficulty in establishing the n=4 algebra in the chiraldrom complex?
I don't know. I haven't tried. There's beautiful work by Sheshani, Elouani, and one other author. Also Frankel, but that's not on the paper. That's not, and Ben Sween, thank you, Ben Sween. That's the name I was looking for. So they construct an n equal 4 superconformal algebra on the chiraldrom complex. They don't claim that it descends to cohomology, and it's a different construction from what you have in Marlikov-Shechtman-Weintraub. And they make a point out of saying that it's a different n equal 2 superconformal algebra that you obtain from that construction. So there's a difference, and their construction seems to depend on the Kähler class. Now, and they also claim... That's right. They also claim that there's no way of extending the Marlikov-Shechtman Weintraub.
But I thought that Borisov showed that it's n equal to 4.
I mean, they claim that you cannot extend this n equal 2 structure to an n equal to 4 structure. And I don't understand. I mean, they don't give any details. I don't understand where the problem is. N equal 4?
I thought.
No, I don't think. I mean, he shows that the cohomology, he argues that the cohomology has n equal 2. He simply states that these fields descend to cohomology. So you start from the given fields and they descend to cohomology. And of course, with free fields, I also know how to extend this to an n equal 4, if that symmetry is there. So I don't know. I haven't done the calculation yet. I literally don't know what the problem is with the extension, but I don't want to claim things that I haven't checked. So I'm kind of not expecting it to be difficult, but I don't know what goes wrong. And people have declared that things go wrong, so I'm being careful here.
So maybe it's a stupid question. If you find the n equals 4 here, what central charge do you expect for this n equals 4? Because we find the characters of n equals 4 in the elliptic genus as central charge 6.
That's the central charge you get here. You get the central charge. I didn't know. I mean, first the topological superconformal algebra, you read the central charge from the properties of J, and that's actually just the central charge that you expect by geometry. So 3 times or 6 times d, I don't know. Yeah. And that's independent of n equal 4. I mean, that's a question that's valid already here. You get the central charge that you expect from a nonlinear sigma model on your Calabi-Yau.